Okay, the 7th of February in the afternoon, slightly after 3:05 p.m. We're going to have a quiz later today, and to get us in the mood for doing that, I'm going to talk a little bit about something that we were talking about at the very end of class last time, and that was the symmetry properties, which I don't think I've really spent as much time on as I could have. This is page 2-39. If you take the Fourier transform integral and break it down, in other words, remembering that it's got this e to the minus j 2 pi f t. If you break that down using Euler's identity, in other words, you would expand that out into cosine 2 pi ft minus j sine 2 pi ft. Then multiply that times x of t. Seems like I have a sign error in here too. You would get that the real part is this piece right here, and the imaginary part actually should have a minus sign on it because of the minus j that's sitting over there. That wasn't the point of my going through this, though. I just discovered a typo, that's all. What I wanted to do was just point out how you can see these symmetry properties pretty much right from these two integrals right here. The overall symmetry property follows from this result down here, but the symmetry properties relating to whether or not x is even or x is odd, controlling whether or not the transform is purely real, purely imaginary, or complex. I guess what I'm getting at is cosine is an even function, right? And sine is an odd function. So if x of t happens to be an even function, what goes on in these two integrals? If x of t is even, in this upper integral, when you integrate an even function times an even function, you have an even function, and you integrate it over symmetric limits, and you get a number, right? It could be 0, but chances are it's not 0. In the lower integral, though, if x of t is even, times sine, which is an odd function, now you have an odd function integrated over symmetrical limits, and that is going to be 0, right? Right. So that's why you can say that if x is an odd function, the Fourier transform is purely real. Likewise, if x of t is odd, then you have odd times even on the top one, and that is an odd function, so that's 0. And on the bottom integral, for the imaginary part, you have odd times odd, which is even, and that's going to be a number or some value as a function of frequency. So that's why you can say that a function, when x of t is an odd function, that the Fourier transform is purely imaginary. So that's that type of symmetry, and that actually is written out over here in this bullet. The other type of symmetry that always applies, though, is that the magnitude response is an even function of frequency, and the phase response is an odd function of frequency. And then another thing that follows from this, which I think is what you were asking me about, Rob, which I kind of spaced out on. Another thing that follows from this is that, and this is regardless of whether or not it's purely real or purely imaginary, is that the real part is always going to be an even function of frequency. The imaginary part's going to be an odd function of frequency. That's now functions of frequency. And that has to do with the way the Fourier transform integral works out from these symmetry properties. That was kind of the other part of that homework problem that I didn't really zoom in on when we were talking about it last time. I'm not as worried about that myself, so that's a hint. That's not on the quiz, because that was a little bit confusing. Any other questions that I've now raised as a result of going through this? Okay.
So is the phase always odd,
Mm-hmm.
no matter what?
It's always odd as long as x of t is real.
Okay.
All this stuff goes away. There are symmetry properties when x is complex, but they're really complicated. I mean, they get a lot more complicated. Usually, if you're taking, well, I'm thinking of when I teach digital signal processing, that book has got a set of properties for the discrete time Fourier transform, which is pretty closely related. And for the general case, the table is, about that long of all these different symmetry properties. For the case of a real signal, it's basically what you see right here on the page. It's very simple. And it's not that you don't want to work with complex signals, it's just that it's messier, that's all. In actuality, maybe you don't care about symmetry all the time. I mean, it's not like the end of the world if there's not a symmetry condition, because if x of t is just something, it's not necessarily going to be an even or odd function of time, and then the Fourier transform is in general complex. So it is. That's just the way things go. I'm going to go back to where we were hanging out before we ended the class. We were looking at the Fourier transform of periodic signals, and we had gotten down to this point where this nice result right here surfaces, saying that the Fourier transform of a periodic signal is just the Fourier coefficients placed on the frequency axis at the corresponding harmonics. And that's a nice result. It's going to get even nicer still. And for those of you in the comm lab, when you do lab number 2, which I guess I should ask, where are you at in the comm lab as of yesterday?
Lab number 2 yesterday.
Okay, so you're going to need this badly then, in a hurry. Okay? And you need autocorrelation function, power spectral density, which is what we're going to get going on today too. It's even nicer when I get through one more theorem, and there's some, that theorem that I'm going to go through is extremely powerful. So last time I talked about line spectra versus continuous spectra, and does anybody have any questions on that? Any opinions? Which is nicer, plotting line spectra or using delta functions? This is like a social question.
I would say delta functions.
Okay.
Discrete is probably easier. Maybe.
The mathematical precision of the delta function, though, is something you can't dispute, right? It just it lays it down. But the problem is you can't really make a delta function. You can only approximate one. But it still gets the point across. Remember last week I was running ADS, and ADS had nice little arrowheads on the top of all those spectral lines, as if to say these are delta functions. Probably because the guy that wrote that module of the software said he knew that this guy right here is what he was supposed to be making it look like. That's what I'm guessing. But inside it was done with a fast Fourier transform and some other math. I'm pretty well convinced of that, because that's just the way a lot of the calculations get done. Spectrum analyzer doesn't do that, though. Those of you in the lab should know that the spectrum analyzer is not doing an FFT or anything like that. It's doing something actually all with analog signal processing, filtering and power detectors and things. Okay, before we get to this theorem, we need to look at another example, and that will help get this theorem set up. The ideal sampling waveform, something that in 2610 we don't go into this because we don't have the Fourier transform ready to go in the first parts of that class. But this is a very handy result once you understand the Fourier transform. And what it says is, if you've got this ideal impulse train in the time domain, in other words, a bunch of spikes, We're talking about a waveform that looks like this. Impulse is spaced every t sub s seconds periodically, and the reason why I call it a sampling waveform, in the front end of a digitizing system, you can think of this impulse train as grabbing samples of the waveform, as if it's momentarily closing a switch, grabs a sample, then opens the switch. And those sample values then get held by the A to D, and A to D converts it to a binary word. Does that make sense? I mean, I know when you work with your microcontrollers, you work with A to Ds, but there's some magic going on in there, right? The A to D doesn't look continuously at that value. It has a clock that comes in and says sample the input, then hold the value, then the sample gets taken the next period, set up by your clock or your timer, and keeps doing that conversion. So mathematically, this is a convenient waveform to come along and form samples of an analog waveform. What we're interested in is, what does the Fourier transform look like? Well, first off, the statement is made right here that since this is periodic, it must have a Fourier series representation too, because it's periodic. So go in and find the Fourier coefficient. Says that you just integrate one period, and that's what I'm doing here, integrating any one period of that waveform. I mean, if I plotted a couple of them on the page, be doing something like this, you might just pick your period like that. So you're grabbing one delta function, and that's what I've done here. I've grabbed one that's sitting at t is equal to 0. It sifts out from the sifting property e to the j at 0, and it comes up with 1 over ts, which is also equal to fs, which is 1 over the sample rate, or sample period. So the Fourier coefficients are identical for this impulse train at all harmonics. So an impulse train sprays out these harmonics at all multiples of the fundamental with equal amplitude. So it's a super harmonic generator, if you could generate a pulse that's skinny like that, as opposed to a pulse train that has finite width. This is like a pulse train that has 0 width pulses. It just makes a uniform spectrum. And if you go ahead and then Fourier transform or plug in those Fourier coefficients using the theorem, or the theory on the previous page that says xn or yn is just the coefficient that goes up to the delta function to make the spectrum, you get this is the spectrum of the impulse train. It's an impulse train in the frequency domain. And then I just drew a picture of it down here. So impulses in time is impulses in frequency. And this is special. I mean, not that it's earth-shattering or anything, but when I was back in graduate school teaching linear systems, one of the professors that taught this said something to me that I've never forgotten. Whether it's just a trivia thing, but trivia in signals and systems is still kind of fun. So there's 3 signals that have Fourier transforms that look like the signal itself. This is one of them. Impulse train in time is impulse train in frequency. There's 2 more signals out there that I know of, and he claimed there was only 3 in existence that have this property. Does anybody want to take a guess? One of them's very trivial.
Is it no signal at all?
Yeah.
Okay.
So a 0, Fourier transforms to 0. So that's number 2.
Okay.
Anybody have any idea what number 3 is? It's one that's not in the book, but it's one that gets talked about maybe in a comm systems class. I mean, like comm 2. A Gaussian-shaped pulse in the time domain. You know what a Gaussian bell looks like from probability theory. Transforms into a Gaussian-shaped spectrum in the frequency domain. Maybe look on Wikipedia or something for a Fourier transform table. It's not on the table I gave you, but you can find it. I don't know if that sounds exciting or not, but it's true. There's a modulation scheme, though, that kind of takes advantage of that, and that's called Gaussian minimum shift keying, which uses a Gaussian pulse shape. It's very closely related to Gaussian frequency shift keying, which is used in Bluetooth. So it does have something that pops up in the original Bluetooth. I don't know about Bluetooth low energy, but the original Bluetooth used Gaussian frequency shift keying, which has a Gaussian pulse shape in it. So that makes the spectrum kind of Gaussian shape then if it has Gaussian time domain shape. But not directly, it's a little bit more complicated than that. Okay, this example I'm going to skip over for the time being. This was something I put in when I wrote the notes because of problems with convolution. I mean, people wanting more review. I'll maybe come back to this if you would like me to. What I'd like to do, though, is go through this theorem right away. This theorem is, to me, it's very valuable, especially if you're in the lab, because it will help you in lab number 2 understand some things. It gives you an exact relationship for getting the Fourier transform and then also the Fourier coefficients as an indirect byproduct for any periodic signal. And all you have to be able to do is expand out x of t as a superposition of periods. So p of t represents one period of x of t, and you just take the periods then and you replicate them with time offsets of the period, and you create the complete waveform. You visualize how that would work. You know, one period, slide it over, another one, slide it back, just replicate them all the way across the time axis, and you've generated the waveform. That's what this says right here. That's not too startling, but what is significant is that you can take your impulse train over here and convolve that with that one period, and then that impulse train replicates when convolved against the period, replicates those periods for you.
So you're creating a periodic signal out of a periodic?
Exactly.
Okay.
Yep. Using the impulse train.
Okay.
That's a good observation, because everything, this is linked to the example I just did with the impulse train. And it's also keys off of convolution in the time domain is what in the frequency domain? It's multiplication. So all we have to do now is just say from the convolution theorem, it's just going to be x of f is the Fourier transform of the impulse train times the Fourier transform of p of t, which we'll call p of f. So the spectrum of the impulse train is just another impulse train in frequency, and you're just multiplying that impulse train times p of f, and p of f might be, in the case of a sinc function, it might be, something like this. But the impulse train over here says you only care about what goes on at multiples of n times fs, so it effectively comes along and samples this thing. So when you have that arrangement of pf times an impulse, you can just replace it by p of f sampled at n times fs, because those are the only values you really care about. That was something that was brought up for the delta function a long time ago. Namely, if you had p of f times delta of f minus f naught, remember you could write that as p of f naught times delta of f minus f naught, because you don't really care what p of f is doing at any point except where the delta function is turning on.
So does that x of t up there, is that a, if you go up, is that the periodic signal that you're creating?
Yep.
Is that what the x of t is
Yep.
now?
Mm-hmm. Just like what you can do in the lab with the function generator.
So the aperiodic signal,
This is the aperiodic signal. One period of the periodic signal is the aperiodic one.
oh, okay.
So this is what the theorem says, and it looks kind of mundane, maybe. Maybe it looks complicated because it has sums in it, but I don't know, to me it's just one of the most beautiful theorems for working through with periodic signals and getting the spectra, because it says don't sweat the details of the Fourier series coefficients, getting the spectral lines, don't worry about figuring out the harmonics and so on, because it kind of automatically takes care of itself. You just look at the period as TS. I just identify one period of the waveform, Fourier transform it, and then I go through and sample the spectrum at harmonics of the fundamental, and then I have to scale it by this Fs, because that came through from the transform pair for the impulse train, and you're done. So a quick little example is right here. This is kind of a fictional waveform. It's a periodic house waveform, if you want to call it that, or top hat or something. So it's two rectangles stacked together, only except now they're replicated, so it's periodic. The period is 10. So you can just whip out the Fourier transform of one period with your eyes closed almost. It's two sinc functions. And then you just drop it into that theorem. You just have to remember that out front here you have to put in Fs, which is 1 over the period. And then drop into here. This is your P of n times, well, I guess I should be calling this F naught in this case. It's F naught. Put in n times F naught, so you're sampling accordingly. So all I did was n times F naught here is just n over 10, right? Because the period is 10. I don't know, maybe this is not just grabbing you and saying this is so nice and easy.
Well, I'm getting confused because I thought you said we were trying to create a periodic signal out of an aperiodic signal.
That's correct.
So why are we starting with a periodic signal then?
Because that's what.
We want to analyze a periodic signal, but we want to analyze it using a technique that involves one period of the periodic signal, which is an aperiodic waveform.
Instead of using a Fourier series transform, you can go about it with the
Fourier,
transform.
yeah, right, and then use this blue boxed equation. So I'm starting with a periodic waveform, and then I study it and I say I've identified one period, and I call that one period P of t, and then I Fourier transform that one period and drop it in, right over in here, and put Fs next to it, and I've got the spectrum, and effectively I've got the Fourier series. I'm going to show you that in a second. Because if you keep your eyes kind of focus on this for a second, this right-hand side of this transform pair, and then if I was to scroll up the page and go back to this, not this, but this garbage I've got to get rid of. Go back to that, what's the similarity? There, that's the Fourier coefficient, xn, right?
Yeah.
And if I go back down here, so that is telling us also that xn is equal to Fs times P of n Fs. Or, to make it look more like Fourier analysis, I should make Fs be F naught probably. I could just say Fs is equal to F naught if I want to call it that. The fundamental frequency, or 1 over the period. Actually, this red equation I just wrote appears in a couple more pages, but I just wanted to write it down to get maximum, hopefully maximum impact. I don't know if it's impacting you or not, but it's just one of these things that can come in handy, especially if you're in the lab. Because you can just, I have haunting memories growing up as an undergraduate of having to do these Fourier coefficient integrals, and they were just a pain. I can remember spending hours and hours doing it. I think it's gotten easier for you guys because EE is such a broad curriculum now that you just don't drill down on any one thing that much, so you're not seeing the individual course pain and suffering probably that I saw. Instead, the pain and suffering you're seeing is this diversity of topics that you have to try to absorb, so you're getting more of a horizontal pain, whereas I had more of a vertical pain. I don't know if there's any analogy there, but this curriculum is spread out a whole lot more than it was when I was in school. And Dr. Zemer, who was my dissertation advisor and mentor, he was even more compact. He took a lot of solid state courses, for example, because that was one of the main things in physics courses. I took a lot of mechanical engineering courses because those were required. You guys, by and large, haven't taken any, right? Where is it going? I don't know, but you're gonna be along the road and see how it changes by the time you're getting ready to retire. You'll say to somebody, or your son or daughter, "So what are you studying?" I used to have to study this, and now it's probably going to be stretched out. Instead of this wide, it's going to be, 2, 3, 4 arm lengths wide of breadth. And the thinness is going to go down even more, because I believe there's a conservation property in there. In 4 years' time, you can only absorb so much. So if there's more breadth, there's got to be less depth. So it's just the conservation is the total area. Does that make sense? To me, it does. That's just philosophy, though, and only, that comes with age, right? You have this thing they call wisdom that you get over time. You don't have that in the beginning, but you get it eventually. Okay, the Poisson sum formula, which I'm not really going to go through, but at the bottom of the Poisson sum formula is where I have this punchline that I was just talking about. So in lab number 2, this is pretty handy. So effectively, I guess what I'm saying is if you do it right, you can kick the habit of having to use the Fourier series if you do it right. But it still exists out there, and it's still a good starting point in the beginning. Okay, power spectral density and correlation. That's a topic that is new to this course that was not covered in any 3205, 2205, and so on. So for energy signals, we had this notion of the energy spectral density, and it was this function that when you integrated it, you get the entire energy. And we kind of saw how to get that. As a matter of fact, G of F we saw was just the magnitude squared of the Fourier transform. But if we have a power signal, we now know how to get Fourier transforms of power signals, but we just can't take the magnitude squared of the Fourier transform of a power that has a delta function in it and instantly have the power spectral density. It has to be done a little bit more carefully than that. Now the notion is, why can't I do that? And you guys are going to want to try to do that, because I remember I wanted to do that too, and it took a long time actually to finally get that straight in my mind. I'm not trying to scare you, I'm just saying there's some concepts that I know just don't absorb quickly. But let's just see where we can go with this idea. So we want the power spectral density. So hanging out there, we've got some notion of what it should be. It should be this function, S of F, if it exists, that when integrated, it gets us the total power in the signal. We also know that the total power in the signal is just the time average. Remember, the angle brackets are time average notation. Remember, that's a shorthand for an integral of a waveform that expands over all time, and you divide by the time you're integrating. So actually, that angle brackets is it's got quite a bit packed inside of it. It involves a limit. So what else do we know we need to have out of the power spectral density? We know that it needs to be real, and it's going to have to be an even function if we're talking about a real signal, and it's going to have to be non-negative. Now, I can justify everything on there, but can you think why those have to be true? Power is watts. It's not stored energy like bars or whatever. I'm not a power systems expert, but some of you probably had that class. So it can't be imaginary power, which is stored in the circuit. It's power delivered actually to a load, so it's got heating associated with it. So that means it has to be real, and it has to be non-negative. If a power spectral density could ever be negative, that would say that we could pass a portion of the signal through a bandpass filter or something just where it was negative, and then we could have negative power flow out of some signal, which is just kind of a bizarre thought, I guess. Rather than delivering power, it would be sucking up power, and that, does that make sense?
No.
To me, it doesn't. So it has to be non-negative. And if it's periodic, then we know that the spectrum is going to have impulses in it. So intuitively, for a cosine wave, we already know what its x of f looks like. What should its power spectral density look like? Well, it should have two spikes in it, one at plus f naught and one at minus f naught. And it should have power in each spike of a squared over 4, because when we integrate that, we'd get a squared over 2. The total power in a cosine wave, remember, in a 1 ohm system is a squared over 2. This intuitively thing is fine for right now, but it doesn't cut it in the general sense. I mean, you just can't live your whole life on intuition. If you can succeed at that with a career, I mean, some people can get away with that. I guess you could think maybe that's how Bill Gates and Steve Jobs became successful, because neither of them got a college degree. Isn't that right? And maybe it was just pure business intuition and find the right people to do stuff for them that allowed it to happen. But I don't think that's true for very many people. So what we need to do is derive a general formula, and the approach we're going to take, because I'm not going to just guess, because I know what I'm going to have to do. I'm not going to ask you to guess and try things. We're going to start with some motivation from the energy spectral density, and then eventually arrive at the fact that what we need to do is start with something called the autocorrelation function, and then from that we'll go to the power spectral density through a Fourier transform. And the motivation for that is to go back to this energy spectral density idea and just suppose that the autocorrelation function corresponds to the inverse Fourier transform of the energy spectral density. So we go in step by step, inverse Fourier transform. So we stop right here. It's x of f times x conjugate of f, because that's what magnitude squared is, right? It's magnitude squared is a complex number times its conjugate. So we have the product in here, and back in the time domain, a product would be a convolution. So we're convolving the inverse Fourier transform of x of f with the inverse Fourier transform of x conjugate of f. But if you go back to the definition of the Fourier transform integral, you find that x conjugate of f is actually the time reversed version of x. So it's x of minus t. So actually we're doing a convolution between x of t and x minus t. So we're not really doing a convolution, we're doing a correlation, is really what it is. Oops. My eraser doesn't always erase. So when you're convolving, when you convolve, you always have one signal times the other one flipped and then slid past and integrated, right? So if you have x convolved with x of minus t, that would say what? You have the waveform. Normally when you convolve, you flip. How can I do that? I usually use my thumb as my timing marker when I'm holding my hands up. That would be convolution, right, of a one waveform times the identical waveform flipped. But in this case, because the minus t is on there, the waveform actually gets flipped back again. So this integral is called correlation, because we're sliding the waveform against itself perfectly oriented, like that. So that's what the correlation is. It's the waveform times itself, and that's That's what's going on here. This is not a convolution because it's a plus sign in there. It's not a minus sign. It's not flipped over. Question?
Yeah, but if we're assuming that the time signal is even, shouldn't x of minus t equal x of t? So then it would be
It's not necessarily even though. That's just one possibility. No assumption there.
Oh no, s of f. Okay.
Yeah, S of F is
That's what I
even.
was thinking of. Okay.
Your head can be ringing though because even odd real imaginary complex is on both sides. It's on the time domain side and on the frequency domain side. But so correlation is a waveform times itself. And this correlation is actually not totally unlike the correlation you talk about in a random variable when you take probability theory. And I think I've asked how many people have taken it already or have taken it already. How many are still yet to take it?
Take it right now.
Okay. So I'm getting ahead of the game when I talk about correlation, but you'll know about correlation here. Correlation now, even without thinking about probability theory, when somebody says correlated, what comes to mind? A best fit. Okay, what else comes to mind?
It's correlated, so
They're related.
Together.
I mean, I could think of it, I don't have a transparency, but if you were holding two sheets together, these are the quiz sheets, so I guess you don't want to hold those up just yet. If I was holding them up to light and looking through them and sliding them back and forth, when I managed to get them to a point where it looks like almost everything is perfectly aligned, that's a correlation peak. And then when I slide it off one way or the other, I don't see as much in common anymore. And that's what the autocorrelation does. It's correlating the waveform against itself. And when tau there is 0, like when my thumbs are lined up and this is the rest of the waveform, it's perfectly aligned. It's not so well aligned. But then we have periodic waveforms. Guess I didn't plug in my power supply. We have periodic waveforms that if you slide it, you'll eventually hit the next period and it will align again, and then slide it further and it will align again. And that's another property of the autocorrelation function.
So does it automatically line up to signals?
It doesn't. It's just a means of characterizing the alignment, and this is the alignment factor right here. Tau is equal to 0 puts them in perfect alignment, but you study the likeness of the signal and itself at different time alignments. The auto means self-correlation, auto-correlating. There's also a cross-correlation. And I better get my power supply plugged in. Have you ever thought about how GPS works? Has anybody ever, some of you have studied it. Does anybody not ever studied or thought about how GPS works? Okay. Well, GPS uses a pseudo-random code related to the ones actually that are in the lab experiment on a microcontroller called a PN sequence, something we're going to talk about. They use a variation on that called a gold code, or at least the acquisition sequence is that. So that's coming down from the satellite, and then in your receiver you have a local copy of that code, and you are correlating it, only it's a cross correlation now because it's the one at the satellite locally with your version, but it's like an autocorrelation because they are identical codes. So the codes are sliding along locally until it gets aligned with the one received, and when it does that, it knows the timing offset that it had to apply to get that alignment, and that's how it factors in the round-trip delay time to the satellite. So a long, complicated waveform can give you, and if it's at a high clock rate, you can use that to get timing. Satellites use that on their own for ranging as well. Satellites have always ranged using some sort of a code and doing a cross-correlation between the local copy and the received copy.
That integral there, is this supposed to be x of tau instead of x of t?
Which integral are we looking at?
It's being convolved, both of them.
Oh, yeah. You're right. Found a typo. T is the dummy variable that has to be integrated out. So yeah, it has to be t. It's a good observation because if I'm integrating over tau, I can't be left with tau, right? That's why I was always taught that the variable of integration is sometimes called the so-called dummy variable, because it's the variable you just place in as a placeholder to use while you integrate. Integration consumes that variable, because that's what integration does, right? You integrate something out, and it's gone. So, more things to fix, which is okay.
There's also true in that blue box as well, right? With BDD.
Yep, because I cut and pasted that when I did this. This is the 4th time I've used these notes, and it's kind of like, okay, there's always something more to find that you screwed up on. No one's ever written a paper though and had it perfect, have you? It's so hard to write something and not make an error, because for me at least, my brain is loaded. This is what's there because it was in my mind before I typed it. Even if I didn't type it, it's still there because it's still in my mind that I typed it, right? It's frustrating. You have to lay off it and then come back. Like, where are these words? Where are these letters? I thought they were there. I'm not a very good typer, so I have this notion that it's there even though I don't see it. I mean, even though it's not really there because I think it's there. So this is the relationship that's been established so far. We take x of t. Here I have the integral correct though, so that's good. X correlated with itself gets us the time averaged autocorrelation function for energy signals. And then the Fourier transform of that brings us to the magnitude squared of x of f and the energy spectral density. So that works for energy signals. For power signals, we just followed the same idea, except we have to compute the autocorrelation slightly differently. We have to do a normalization in there. Yeah. Got to watch the clock, and I forgot my watch. So the autocorrelation function in this case involves dividing by t, because that's how we get a power signal. Just like we got the power, average power by dividing by t when we define the time averaged autocorrelation function. Now it's defined in these terms. This special case is the one that applies frequently for our applications. Actually, it applies always for our application. We're not going to see any signals whose power spectral density we're interested in that are not periodic. In my other class on statistical signal processing, we'll deal with that, but that's because we're dealing with random signals, and random signals is the next stage in learning beyond random variables. You know, first there's probability, then there's random variables, and then you get into random processes.
So even the pseudo stuff in the lab is just it's
Periodic.
It's
Mhm.
it's trying to mimic a random.
Yeah, I mean, yeah, you're going to do an experiment where you replace the pseudo-random generator using a rand function in C, but that repeats too. The spectrum will be so dense, the lines will be so close together, you won't be able to zoom in on them if it's a good random number generator. But it still has a period. It's just the period is just, you know, huge. And getting back to GPS, the acquisition code for GPS that the commercial GPSs use is short. The one that the military uses clocks at a higher rate and has a period that's, you know, classified, and it's very, very long. So the spreading code that's used in cellular telephony is set up the same way. It's known, but it's very, very long. So everybody can share the same code. They just get a different time offset into that same code. And your signal looks random compared to somebody else's because you've got a different piece of this big, huge code. And it's programmed into your SIM card of your. That's what makes your phone's code unique. If it's a code division multiple access phone, which virtually every phone uses that now. And that relies on correlation. I mean, no correlation, no match, correlation match. Okay, so what do we have here from the time average autocorrelation function? We have immediately that if we were to take our notion of power spectral density, which we haven't quite defined yet, and integrate it for all frequency, that would be the same as evaluating Rx at 0, which is the average power. That combined with the definition and combined with the fact that for energy signals we know that the Fourier transform of the autocorrelation is the energy spectral density just points, this is not a rigorous proof, but just points at the idea that the power spectral density is the Fourier transform of the autocorrelation function. And remember, do I have a picture? So formally, and this is for the random signals case, which actually relates to the time average case we're looking at right now, this is the way you get power spectral densities. You have to get it by processing through or passing through here, and then finally you can get to the power spectral density. So if you have a waveform that's periodic, you get the power spectral density by first getting the autocorrelation function and then getting the Fourier, taking the Fourier transform and getting the power spectral density. Now, the good news is, though, is there are some ways of short-circuiting this a little bit for periodic signals. The energy spectral density case, just to point out, you can take this pathway right up here and go right from the time domain. So it's easier to work with an energy signal, but for a periodic power signal, it's a little bit harder. But it's not really that much harder because of that theorem we were looking at a little while ago. That theorem also helps out immensely in this case. It's another reason why it's pretty handy. It doesn't work for every signal, though. It works for some signals where it's easy to get the Fourier coefficients with that theorem. And I'm going to try to, before the quiz starts, explain that. So what are some properties of the autocorrelation function? R at 0, 0 lag, has the waveforms aligned, so that is equal to the average power, and that is also the largest value of autocorrelation function in magnitude. And that kind of makes sense. When you're perfectly aligned, you've got the most correlation. If I lag that way or lag back that way, I can't possibly have as much correlation as if I'm right, perfectly aligned. Autocorrelation function is even, so if I slide one side or the other, I'm going to get the same value. And this is for real signals. Again, I didn't say that in here, but it's for real signals. And another thing is that if I take the limit as tau goes to infinity, I'm going to get the squared value of the mean as I lag. And lag is just another term for saying what tau is. It's sometimes called the lag value. 0 lag is perfectly aligned. Lag going to infinity would be like that. Minus infinity would be like that. How much one signal is lagged with respect to the other one. So when I increase the lag value to infinity, the waveforms, if they're not periodic signals, there's basically no alignment between the waveforms at all anymore. So there's probably no features that are uncommon, which means that the autocorrelation function is approaching the average value of the waveform squared, which is, this is another name for this would be DC value squared. Because the AC part of the waveforms are totally uncorrelated and they're not going to contribute anything, so all that's going to be left is what is in the DC component of the signal. However, if it's periodic, and that's the case, like I said, for this class, predominantly when we use these ideas, then property 4 says you get a periodic autocorrelation function. So the waveform periodicity pops up in the autocorrelation function. And that makes sense. You slide one whole period and you're going to be correlating with the same period again, right? And it's going to peak back up again. So the autocorrelation function goes up and down over time. The Fourier transform of the autocorrelation function is the power spectral density. This is probably the huge punchline right there. That's the main thing we were into this for. And I'm just pointing out in random signals, this is one of the key things in the graduate class I'm teaching on Monday nights, statistical signal processing. Okay, now that we have this framework, let's see if the original intuition holds true. In other words, intuitively we said the power spectral density of a cosine wave should involve two spikes with a squared over 4 as the spectrum or the power on each spike. So formally, starting from scratch, find the autocorrelation function. I have to plug in two waveforms. I have to plug in x of t and x of t plus tau, and then integrate, and I'm using the right variable there, dt. And because of the fact that it's a periodic waveform, I just need to integrate over one period, and then I normalize by one period, t naught. So I multiply those two waveforms together, and something very nice happens. I have a trig identity, right? Cosine times cosine is the sum of the arguments and then the difference of the arguments. And a 1/2 factor too. That's back in the appendices. So what's neat is that this is the difference term. And what happens in the difference term is that t goes away. So you're not integrating with respect to t, you're integrating with respect to t, so with t gone, it looks like you're just integrating a constant, and it gives you that for the autocorrelation function. So it's just a squared over 2 cosine 2 pi f naught tau. Now I didn't explain what's going on over here, but this term goes away. Why does it go away? It's because t is sitting in here, and actually there's a 2 in there as well. So actually the frequency of the cosine wave is 2 f naught. So 2 cycles of cosine are sitting in that one period t naught. And what happens when you integrate integer cycles of a cosine? It always goes to 0, right?
Yeah.
So this term is gone. So there's the there's the autocorrelation function. Just as a quick check along the way, one of the properties of the autocorrelation function was at 0 it's supposed to be the power, right? That was the time average power. And sure enough, it's going to be a squared over 2, so that's good. It's also periodic, so that's good. And the fact that it's periodic, something like this on the tau axis, that period and one period later, one period back, it's maxed over and over again. It doesn't violate that property. The property said at 0, at lag 0, it would be greater than or equal to any other value of the autocorrelation, and this doesn't violate that. It just equals it. And it's periodic, which is what it should be for a periodic signal. Now when you Fourier transform that cosine using the tau as the equivalent time variable, you do indeed get the a squared over 2. This is from Euler's identity of expanding out the cosine, a squared over 4 then, and a delta at f naught and minus f naught. So this is now tied to math theory rather than just simply intuition like it was at the beginning. Here's a couple properties that are kind of like those Fourier series properties that I had earlier, where I'm just considering what happens if you shift a waveform by adding a constant to it, and what happens if you time shift the waveform. What does that do to the autocorrelation? So if you amplitude shift a waveform, the autocorrelation function still comes back through, and all you're going to get here is a change in a constant value. So it puts a pedestal on the autocorrelation function. The a squared pops back through, and then you get another term that's related to the DC component of the waveform itself. That doesn't alter the shape in terms of the actual shape, it just raises or lowers the autocorrelation function. And if you were in the lab looking at if you're looking at the power spectral density, which would be the Fourier transform of this, those constant terms are what in the frequency domain? DC, and on the spectrum analyzer in the lab, you don't see it. So if you had a logic signal that you were looking at, like from the microcontroller, it won't matter whether the waveform is centered about 0 vertically or whether it's sitting up here at some high logic swing or low logic swing. You'll only see the AC spectral lines. So don't be confused. That's what I'm saying. Time shifting the waveform is even nicer still. It doesn't alter anything, because if you go through the math here with the time average and then do a change of variables in here, you see that they're equal. And this is a property that's called being blind to time offsets. And it's not really all that surprising. It just says that the autocorrelation function can't show you the absolute time. I'm not saying you can't use the autocorrelation function as a means of finding time of arrival, though. I'm just saying the autocorrelation plot itself won't, but when you're doing it like in the GPS, you know the alignment that you had to bring the local code to get the correlation peak, and that's the key right there. Where did you have to set your local code time offset wise to achieve that peak, autocorrelation peak, and then that number gets stored and computed to get, eventually go through the latitude and longitude. It's more complicated than that, but the satellite also sends down what's called the ephemeris data for its particular, the Air Force calls them SVs, SV 1, 2, 3, 4. SV is space vehicle, that's the terminology they use. So each satellite has its own code that it uses, and you lock onto it. You know what SV number you're locked onto because you can only lock onto it with its code. And then it has its ephemeris data, which comes down along with it, which tells you exactly where that satellite is over the Earth, because it's keeping track of that on its time base, and it sends that information down on a low-speed data link, which it's only 50 bits per second. That's how fast the ephemeris data comes down. That was part of the design, though, originally, to make sure you could get that, which I think explains why GPS receivers don't lock really fast. I have one for backpacking, and when I first turn it on, it has to acquire all the satellites. It takes a long time to finally get my fix. But then if I just turn it off and turn it back on again, maybe within an hour, just to check my latest fix, it acquires very rapidly because the satellites are still roughly in the same position, and it can get the fix pretty fast. But if it's a cold start, it takes longer. Maybe you've noticed that in your cell phone too. But actually that's not true of your cell phone, because it's always trying to talk to or listen to the satellites as long as you're exposing your phone to the outdoors. Indoors it will lose track of where things are. Question?
Yeah. I just wanted to know, should there be where should the inner parentheses be up there? RZ of tau equals, that's the right side of that, equals x of...
Oh, I see.
Yeah. Okay, that's what I thought.
Right in there. Yeah. Sorry about that.
Sure.
Okay, we're going to do sum of sinusoids, but we're about ready to take the quiz. This is what you also get into in the lab, and this is a problem in the homework assignment number 2, pseudo-random sequence generator. And this is a variation on this is what creates the acquisition code, the gold codes used in GPS. It's a maximal length sequence generator, and this is in hard digital logic what it looks like. You can create it with some D flip-flops, and then you have an exclusive OR feedback mechanism that comes around and connects to the first shift register flip-flop. In this case, because it's got 3 flip-flops and the feedbacks here are connected to the optimal points along this 3-element shift register, it generates what's called the M sequence, where M stands for maximal length sequence. And the maximal length you can generate with 3 stages is 2 to the 3 minus 1, or 7. So the pattern it generates is a 7-bit long sequence, and then it starts over again. If you had a 10-stage generator, which is what the GPS shortcode uses for what's called course acquisition, that generates a 2 to the 10th minus 1, which is 1023. So that's the code that you're acquiring when you're acquiring a GPS signal. You're acquiring a 1023 chip long, it's called chips in spread spectrum, or bits sequence. Now, here's the deal. If you want to get the Fourier transform of this over one period to get its spectrum, that's kind of a not such an easy thing to do. If you think about a 1023 long pattern of 1s and 0s, you're going to Fourier transform that as one period. You can't. It's too intense. What you end up with, though, is you use this property that its autocorrelation function is a periodic triangle autocorrelation function that has this appearance to it. And in the lab, and I'll post the solutions for the homeworks so that you'll have an easy grasp of what you're going to be seeing in the lab, you use this result here and Fourier transform this, and then go to the power spectral density. So this is a little bit of a twist over what we were looking at earlier, but this same theorem is very, very useful. There's a little bit more, but I got to hand out the quiz, so